All right, guys, we're gonna do so it's circular motion. All we've done so far is what we call linear motion. We're going left and right, up and down. We did do projectile where you're going forward, up, and down all at the same time. And then the last one for us is this circular motion. These are the equations. We're just gonna focus on the ones on the left, which are really variations of equations we've already done. So, and I'll talk about these more in more detail when we get to those slides. But this first one here, the v equals 2 pi r over t, should should look like v equals d over t to you. AC equals v squared over r is new, um, but it's how we're going to get this thing we call the centripetal acceleration. And then sigma f equals mac. It's our old friend force. It's not as bad as forces. There's really just one force equation I'll show you. So if you can get that one, you're good to go. And then the gravitational one is if you're uh, talking about orbits, stuff like that. And then depending on time, we'll get into some of this. But circular motion um, is everywhere. I mean, it might be more common. We don't typically go in a straight line. We eventually have to turn, and then that's when you get that potential of circular motion. And then, like it says, from planets orbiting the sun, cars taking curves, spinning, gymnastics engineers designing turbines. Understanding it helps professionals, again, control and predict the systems. We can, uh, we know what's going to happen before it happens, that kind of deal. All right, those are the equations. And then just to introduce it, that car right now is in projectile motion, right? That car, it's as you come over it, don't do this, but as you come over, if you were to come over a hill fast enough, you have the potential of launching the car like off a ramp. So it'll tell you where it's gonna go or like where it's gonna land, but it's not gonna tell you like it says how fast can you go so you don't fly off the road. Like when you're going around a curve and you see those signs that say go 25, like how do they know that? To determine the speed needed, yeah. Um, so to determine the speed needed to not leave the road, that's the unit we're on. That's circular motion. All right. So the demo, unfortunately, um, I'll see if I have a video of it, guys. I'll try to add it in, but it's just this toy pig that flies in a circle. And then the question is, what is causing the object to fly in a circle? Well, it's tied to you can see in the picture there, it's tied to a string and then it's has these wings that pull it or push it around. I'll try to add the video, but it's doing it in what we call a uniform, what we call uniform circular motion. So it's just doing this, nice and steady, nice and steady. So is the object changing speed? No, it's going in uniform motion. That's constant speed. Is it changing direction though? Yes, it's constantly changing direction to go in a circle. So is the object accelerating? Yes. And then we'll talk about the acceleration in a second. You can feel it. When you go in a circle, you can feel it. Even though you can go at a steady speed, it doesn't because you're changing direction, you have a change in velocity, which means you have a change in acceleration. Um sorry guys, more demos. Sorry. All right, what direction are you being pushed when traveling in a circle? Um and I'll give you examples. It's nice to show you, but I can also give you examples. So so the question is, you're going in a circle, and then as you're going in that circle, you kind of feel right. You feel like you're being pulled outward. When you take a curve to the right, you feel like you're getting pulled to the left. When you do the opposite, you feel like you're getting that way. Um, so when going like in a merry-go-round, when you're just going in a circle, you feel like you're getting pulled in the A direction. Um, but here's where we got to stop and think for a second. When we go in linear motion, when we go straight line motion, you're just driving straight down the road and you hit the brake, your body goes forward. But the acceleration on your car was actually backwards because it slowed your car down. You went forward though. When you hit the gas, you go backwards. But the gas actually the tires actually pushed the car forward. So the force, the acceleration was forward, but you felt the opposite. So what direction must oh sorry, that's not there yet. So what direction are you being pushed when traveling in a circle, A or B? Well, it's the opposite of what you feel. So you feel A, but you're actually being pushed in the direction of B. And I'll give you the example here is in a car and you want that car to go in a constant circle to the left, right? You would turn the wheel into the center. You don't turn it out. If you turn it out, you're going to go out of the circle. If you keep turning it in towards the center, the car will go in a circle. So what direction are we actually being pushed is in towards the center. And we call this the centripetal force. We also call it the centripetal acceleration. Centripetal is just a fancy word for center seeking. I think it's Greek, maybe if that helps anybody, or Latin. I don't know its roots, but it's something with center seeking. So it's a center seeking force. It's a center seeking acceleration. So we define it as an inward acting force that causes an inward acting acceleration, or center seeking if you prefer that. Hence the centripetal, and it's caused by other forces. The what we call the centripetal force is caused by other forces, and we'll talk about that more when we get into the problems and stuff. Centrifugal though is probably the word you've heard. I feel like when if you're reading a book or something and it talks about a rotating object, there'll be like the centrifugal force. It is the feeling, right? So the F in that centrifugal is a feeling of an outward force, and it is fictitious. There isn't actually, so think about that the last slide here. Nothing, when we were going in this circle, there was nothing outside of us pulling us outward. Our body just wanted to go that way, which I'll talk about that. That's the next slide. But um, nothing pushed us that way. We feel like we're getting pushed that way, but we're not actually being shoved that way. Mathematically, it does work though. It just doesn't answer why they move to the outside. It's not an answer for why. So mathematically, it works. And but when we're doing these, we're going to think again centripetal force. Centrifugal is just one of those words that it caught. We thought there was an outside force, and it feels like an outside force, so it's stuck. And then now it's kind of synonymous. I don't know. I'm gonna go with synonymous with centripetal, but they're two, right? Centripetal is the actual center seeking. All right, which of these forces? So the example here. So which of these forces explain why you slide to the outside of the circle? It turns out neither one of them do. As you're going around this circle, right, you're going to the left. Everything in your car feels like it's being pulled to the right. I think that's a cup of coffee in there. I don't know why you would just sit a cup of coffee on the dashboard. But cell phone. Let's just say you had your cell phone sitting on the seat beside you. You turn the car, right? You feel like you're getting pushed this way. The cell phone slides across the street. Did anything actually push it across the street? The seat. No, nothing touched it, right? The centripetal force on the car moved the car this way. Why did all the objects inside the car go this way? And we'll talk about it on the next slide, but it's called inertia. They just wanted to. The centrifugal force is how people would explain that, though, but it doesn't explain it. It doesn't say. People know what you mean, but they don't know the why. They're like, oh, the centrifugal force, but they don't. There's no why there. So the centripetal force had you going in a circle this way. The objects moving across the car is inertia, not the centrifugal force. So be cautious. You'll see in multiple choice questions where it'll be the centrifugal force. It's not. Unless it specifically asks what is that fictitious force or that mathematical force that you feel, then you can do it. Sorry guys, video. But this one I can explain. And I think some of you've done this. Have you ever had like a bucket of water um, and you spin it upside down? The question is, why doesn't the cup well, in this case, my example, why doesn't the water come out of the bucket? And then man, I keep giving you more examples and I'm not getting to the answer. Here, one more example. Why does the roller coaster not keep falling off? Not keep falling off. Why doesn't it fall off when it's at the top of the loop? So what force keeps the coaster from falling? Um, Centripetal force pushes it in a circle. It does not keep it from falling off. And then the expanding ball demo, it's those silly. They're compact and then you can pull them out. If you have one of those, when it's in its compact mode, like spin it real fast. Like try to spin it on a hard surface, it'll pop open. And we'll talk about why. Oh boy, We are eventually going to talk about why. I'll come back to that. Did I seriously skip it? Huh? Sorry, guys. I must have deleted the slide. Here, we'll talk about it now. Um, yeah, sorry, guys. It's called inertia. Objects want to do what they were doing. So we've talked about it before. I was waiting for a slide where I said the big reveal. And I don't have one. But anyway, as this coaster's going around, it wants to follow that green arrow. So as the coaster's going around, it wants to follow that green arrow. So everybody in that car also wants to follow that the direction of the green arrow. Um, the track though is pushing it inward. So as the coaster, let's say my hand's the coaster and you're the person in the seat. As you're coming around, let's see if I can do this. You want to go in the direction of as you're coming around, right at the top. Let's just do right at the top. My hand's the track. This is the coaster. The coaster wants to go straight, but the track pushes it in a circle. And so pushes it towards the center, and you get this motion. But everybody inside that car wants to keep going this way. So its inertia has it riding up against the track. Not that it was pushed into the track. It just wants to go straight, but because the track is there, the track pushes it back to the center and it goes in a circle. Um, so the reason why things can go upside down and not fall out is inertia. The reason when your car turns and everything in the car goes one way and the car goes the other is inertia. You just want to go that direction. Objects want to retain their motion. Um, the competition game. Let me know if you want this. I can't remember if I think I put it on your class kick. I'm not positive. I kind of shortened your guys' class kick since you're not in the room. But it's a little simulator. I want to say it's on there, but you'll so you're gonna take what I just described and you're gonna use it to play a little game, and then you just screenshot your score. You can go for the record. Were these both 2024? 6,486. I can't even get 6,486. I don't even know that I've broken 1,000 on this game. So, but if you want it, if it's there, obviously just play it. The score doesn't really matter. I just want you to get you. How do you win the game? Is the point? All right, tangential velocity. Um, this is we're in the. Oh, this is the first. Yeah, first equation. Sorry, guys. Lost my place. So tangential velocity is how fast you're going tangent to the circle, so sideways, perpendicular to the circle. Linear velocity of an object moving along a circular path. What direction did the car travel once the centripetal force was removed? And then this is the game that you're going to play. But if you're going in a circle, how can I do this? If I'm going in a circle, and then all of a sudden right here, I just cut the string or remove the centripetal force, I'll go straight up, right? If I'm right here and I cut the string, I'll go straight up. That's the tangential velocity. Um, and then the equation, so how fast are you going is distance over time because you're going in a straight line. Once you cut, it's the sideways speed, right? That's a straight line. So that's v equals d over t. Now our distance though for a circle is the circumference. And so all we're doing is changing d to 2 pi r, which is just the circumference of a circle. So it's all radius based. Radius of the circle. If you have a bigger radius, you got to go fast. Well, you got to, if you want to, yeah. If you got a bigger circle and you want to stick like a track, like the track runners. If you're on the inside track and they're on the outside track, right? That inside track has a shorter distance than you do on the outside track. Um, oh, and then the t, the time for circular motion because it's uniform, it's repetitive. When anything's repetitive, we don't have to look at the total trip. We can just look at one rotation, and so we call that the period. That's the capital T. So the capital T is the period of one rotation, and that'll come up in the lab. The factor of change questions real quick. Um, what happens to the period if the radius is doubled? So you double the radius. The factor of change ones, it's been a while since we've done these, but anything that doesn't change becomes a 1. This is a little math shortcut. Again, I can show you the longer way, or you can go back and watch the Edpuzzle factor video if you really want to. But the 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 shortcut way is that basically you're dividing the initial conditions by the final conditions by the initial conditions, and things cancel out to 1. So because 2 always stays the same, it becomes a 1. Pi becomes a 1. Now the radius doubled, and then I want to keep the velocity the same. What happens to the period Actually, it doesn't say anything. Factor of change when happens to velocity if the radius is doubled. Anyway, oh, sorry. So what happens to the period? I'm trying to figure. I thought I had this going for you guys. If the radius is doubled, this is the second one. The first one would be sorry, I thought I had the first one a picture for you, but the first one, if I double the radius, and then the constant velocity, I should have mentioned something about the tangential velocity. Let's say that stays constant, then that also becomes a one, and so I would take t to the other side. So if r doubles, then the period has to double. If I'm going the same speed around a twice as big circle, it's going to take me twice as long. I just noticed that I'm in a little circle down here. What happens to the velocity if the radius is doubled? Now here, let's just say the period stays the same, and I increase the radius. This one's a little more straightforward. I don't have to rearrange the equation at all. Then the two and the pi don't matter. They cancel each other out. They don't cancel each other out. They get canceled out by themselves. So what happens to the velocity? It would also double. There's my, I don't know why I have it for B and not for A. All right, we're getting there. Sorry guys. So here the I don't actually have the record player with me. Where does the record player have the greatest centripetal acceleration? So instead of a record player, picture yourself on a merry-go-round. I don't know the last time you were on a merry-go-round. Also, they're getting harder to find for obvious reason. They're not the safest thing. So how do I want to do this? So we'll go through the equations. So v equals 2 pi r over t. That's the one we just talked about. That one's v equals d over t again. So that one shouldn't really trip us up, except we need the radius and the period instead of the distance and the total time. And then AC, what we call the centripetal acceleration, you just take that v that you found first, the tangential v, and square it. And then you divide by the radius. That's what we call the centripetal acceleration. And then if you want the sum, right, the sigma's the sum of all the forces causing that motion to go in a circle, you just take A and multiply it by the mass of the rotational object, or U if you're looking at U. And then there's a good picture of this. Here's the tangential velocity is this blue arrow. The centripetal force and acceleration are in towards the center. There is a third thing called omega here, and then that's the actual rotation. That's what we call so there's circular motion and there's angular motion. If we have time, we will talk about angular stuff. But for now, we're gonna focus on the outside, the more the linear stuff, tangential, I should say. What will happen to acceleration if the radius is doubled? So this one's very specific. It says careful since velocity is not constant. We did the example if it was constant. What will happen to the acceleration? So we're over here if the radius is doubled. Well, if I double the radius, right, that's going to half the centripetal acceleration. The problem is it said v is not constant, so then I got to come back here, and this is as tricky as it gets, and I got to double the radius back here to see what actually happens to the velocity. And we did this one, right? And again, I should have been more clear that the period stays the same. These aren't answerable unless certain things stay the same. Or they give you more information and tell you how they change. But so let's go the easy route and say it doesn't change. When they leave stuff off like that, just go with it doesn't change. So 2 pi and the t all become 1s. So if I double the radius, I double my velocity. So then I come back over here to the AC equation. Well, if v is doubled, v is going twice as fast in this situation. You have to square it. So it's 4. You get 2 squared, it's 4 on top, divided by the doubling on the bottom, you double your centripetal acceleration. So what will happen to the acceleration if the radius is doubled? Because you also doubled your speed, you end up doubling the centripetal acceleration. And then you can ask another question. So what happens to the force you feel? It also doubles. So when you go so you're in the center of a merry-go-round, that radius is 0, you got nothing. You have no centripetal force, no centripetal acceleration. Take a step to the middle of the merry-go-round. I'm sorry, you're in the middle. Here, I'm going to use my circle down here. You're in the middle, go out almost halfway to the edge. You'll feel a force. Double that distance and go to the edge, you'll feel twice the force that you felt when you were halfway. That's the silly factor of change. You can do it with numbers and stuff, whatever works for you. I think it pops up in a couple concepts question. Is the Earth throwing us off? We will talk about that for a split second. So here, the problems in lab are coming. there's two labs. You're only going to do one of them, so it might not be this one. But anyway, is the Earth throwing us off? The Earth is rotating, right, like a merry-go-round. When you're on a merry-go-round, do you feel like you're going to get thrown off? Yes, right. So the Earth's rotation is actually throwing us off. It's not a lot though. It's like half a pound, like something silly, but it is trying to throw us off. And then the why do sorry, I'm trying to usually I label these. Oh, explain stat, here it is. Sorry. Usually I leave myself little notes to talk to you about. Is throwing us off, right? So the Earth is throwing us off because it's rotating. Anything rotating is actually trying to throw us off. Explain Saturn's rings. Um, the rings formed where Saturn is rotating the fastest. So some of its material that did not coalesce into the planet got flung out, right? Like when you toss a pizza up in the air, and in the crust, not the pizza, but the crust, right, spreads out. Um, that is what's happening with Saturn's rings. It's spinning. And also, our planet is in a perfect sphere, right? It's bulged in the middle because it's rotating. The orbital plane. This is this picture here. I covered it up a little bit, but for the most part, if you had your back to the sun and you just looked out across the space, the planets would be pretty much lined up, not like plane wise. There are a couple of them that are off. I can't tell. Oh, Mercury is way out here. Sorry, I covered up Mercury. Um, Whoops, sorry, I keep moving the button. My point is though is that when the sun was forming, it was rotating, and all that matter in our system um, started to spread out, and then chunks of it, right, were more gravitationally bound, were closer together, and so gravity started pushing those together, and you got the planets. Why they're on the same plane is because the system, our sun, is actually rotating, and so the objects orbiting around it are also rotating with the sun's. You guys, I'm sorry, we're on circular motion. The record player. Real quick, this is the rest of these slides are kind of application of all rotational motion. Um, so some of our earlier storage devices were rotating. And then there was so record players real quick. They're interesting if you've ever come across one. The needle vibrates in these little grooves, and then that needle's hooked to a magnet, which this coil of wire picks up that vibration from that magnet and can translate it to sound through a speaker. But it's a rotating disc. And then how does the speed at the edge of the disc compare to the speed near the center? And it's just like the merry-go-round. The outer edge is further away, so because you have to travel more distance, because of that bigger radius, you have to travel more distance. You have to travel more distance. You have to go faster, since the whole disc is uniformly rotating. As you go in, it slows down. So then, how does a record player handle that? Well, it can't. It's a uniformly rotating object. So record players actually had to change some of the songs towards the end of the track. So it's as it's working its way into the smaller tracks, um, had to change their sound a little bit because it couldn't pick up. I think it's the high frequencies. Here we're getting into outside of physics, but well, it's physics, it's sound, but it's outside of me. I'll put it that way. I think it was the higher frequencies it couldn't play. So some of those songs towards the end are more ballady. Um, but it's something to look into if you're interested in the in music and records and that kind of storage, that kind of thing. So we call that analog. I'll talk. That's the next slide. Sounds. Some of the argument for it is it's actually recording uh, the actual sound. Like it's not converting it to anything. It's actually taking that sound and just etching it into a track. So the argument is, so some people say it sounds more real. I'm going to talk on the next slide. But read by a needle. CD players are interesting. They also, right, the CD players also get smaller. The tracks, DVDs, Blu-ray, all that stuff. The tracks get smaller as you come. The speed slows down, but CD players can actually adjust their speed and still read the information without problem. So it was just record players where they didn't adjust the as that needle came in, it kept the same constant speed. But digital versus analog, real quick, how we store data. So records are something we consider analog. Like you take the actual sound and put it on a disc. Uh, the idea with digital is we record. Was there sound there? I'm kind of simplifying this down, but was there sound there? Yes, we store that. Was there no sound? Then we don't store it. So we have It's like true and false, one and two. It's binary code is where we're getting into. So it's on off, true false, zeros and ones in this case. Um, however you want to think about it. But digital, um, and this is just a cool picture. The analog is this smooth, continuous representation of the sound. It wouldn't be this nice, but this is just one. If we were just playing one frequency, it would look perfectly smooth on an analog scale. If we digitize it, when we had the old 8-bit, it was very chunky. We went to 12 bits, you can still see the chunks. Now 24 bits, 48, right? It starts to smooth out, and we get to a point where digital and analog become hard for us to decipher. I'm sure there's some music people that can still do it, but oh, sorry, that's
Now let's hear about the decrease in information.
sure. It's worth watching. Hopefully it doesn't flag me for that little bit. Um, and then cotton candy, again, like I said, these are just applications. All the cotton candy machine is doing is melting that sugar and spinning really fast. And then there's perforations in the side, right? If you've ever been on the ride where the floor drops, I don't. Usually it's at fairs, which I question, but just for safety. But anyway, the it's the ride where the ride's spinning and you're just standing on the outer wall and you feel like you're getting pushed up against the wall. Again, it's your inertia. But cotton candy machines do the same thing, except they're in the middle. There's this hot thing that's spinning, and that hot melted sugar gets not pushed, right? It's not getting pushed. It's a centripetal push. Like it's getting pushed towards the center, but because of inertia, it wants to travel outward. Same reason why sorry, another one popped in my head. Why the laundry washing machine can dry your clothes and there's holes on the side, right? Um, the water wants to go in a straight line. Sugar does the same thing, the melted sugar. And as it goes through the air, it cools real quickly and crystallizes. And then that's where you get the strands of cotton candy. Uh, so causes of centripetal force. Um, sorry, I probably should move this slide. It's in a weird spot. Is centripetal force is not an actual force. It's the sum of all the forces acting on it to make it go in a circle. So if you're just on a flat road turning, it's friction. Friction is what's causing you to go in a circle. In a banked curve like this other picture, so now you're on the side and you got a little bit of a push this way, then it's a little bit of gravitational, normal force, friction, like you got all that stuff. You can spin stuff on a string like a sling, and then it's tension. um, oh, roller coasters going upside down, right? Gravity's pulling you down, but you're pushing up against that track. That's the normal force. Or going down at the bottom, you still have the same problem. Gravity's pushing you down, and the normal force is pushing you up. um, so we got uh, all these are actually the sigma F. Unless it asks for the sum of the centripetal forces, then you would find sigma F. Otherwise, you're going to take sigma F and change it to normal force and gravity or tension or friction. But we'll do those together. I'm just giving you a little heads up. That slide's, I think, in the wrong place. I got to look at my slides again. Circular motion and gravity. If you're talking about satellites or planets orbiting, that's a rotational motion. It's not perfect, right? Some of the planets are more circular path than others. But if the planet's pretty close to a circle, these will work. Um, or like we put our satellites into a circular orbit. Elliptical orbits, that's a little more complicated than this, but same idea. You got a gravitational force causing the centripetal force. So you don't say Fc equals ma. We change it to Fg, and then Fg is that gm1 m2 over r squared. And then you set it to ma. But we'll talk about that when we're doing all the problems. G4 force experience in terms of acceleration due to gravity. So sometimes you'll hear them referencing G forces. 1G is what you feel right now. It's your weight. Like you feel that every day, 1G. It's when you go up and out. And we kind of talked about this in forces, but we talked about it in terms of acceleration. So I would like your acceleration would make your weight change. We can specifically relate that to gravity. 1G, right? G is 9.8. 1G, you're experiencing 9.8 meters per second squared. 2Gs, you're experiencing twice that, so 19.6 meters per second squared. 3Gs, 4G, you get the idea. It's twice your weight, 3 times your weight. Um, but that's the G force. So sometimes in circular motion, we describe that force that you feel as a G-force. Oh, don't play. Sorry. There's videos of training the pilots when they put them in the rotation. And also, it's like the scrambler at the amusement parks and stuff where it spins you real fast in all those directions. Um, that you experience a G-force that way, which is the precursor to artificial gravity. If we could spin the space station, or if we design the space station to spin, we could create artificial gravity. Um, where are we at? What is the ideal acceleration and what can be adjusted? So here's where it becomes a problem. Earth has one, like, why don't we just do that? Well, so one rotation on Earth is 24 hours, right? It takes 24 hours to Earth to rotate. That's a rotation. That's an RPM. This is rotations per minute. It's not even one rotation per minute. So it's 0.006. That's for the Earth. So let's just say we went to one rotation per minute, right? The Earth doesn't even get close to one rotation per minute. Let's just say we went to one rotation per minute. It'd be a mile across for an ideal situation. For an ideal situation, that thing would be huge. I don't know if you saw Interstellar, like that space station at the end was huge, ridiculously huge. Um, but it could handle up to, oh, here, we could handle up to 4 rotations per minute, and then it would still be big though, size of a football field. Some of the problem is if it's too small and our feet are down here in this picture. I'm looking at this picture here, and we're just manipulating AC equals V squared over R. Like if you want a certain acceleration at a certain velocity, tangential velocity, rotation per minute, that you're going to affect the radius is what's happening. But if it's too small, we get our feet at a different gravity, artificial gravity than our head, and it would be you would have problems. It would be a sensory um, issue where you feel different pulls in different parts of your body. Like it wouldn't be comfortable. Class kick. Are we on the last slide, guys? Desmo. So we'll all do. Yeah. All right, guys. This is stuff we'll do throughout the week, and I'm gonna stop.